Hello and welcome to my channel, and as you all know, we are doing the problem session, and in this problem series we have already completed 8 problems and our topics remained resonating structures, stability of the resonating structures, rules to write resonating structures, aromaticity, carbocations, carbene ions. Right now what we are looking at is a very important topic called as steric inhibition of resonance. The meaning of this topic is because of size issues, because of steric repulsion, the resonance cannot be availed. The resonance is prevented. So the meaning is because of certain tussle, because of certain repulsion, the condition of resonance is not met. The condition of conjugation is not met. The orbitals should remain parallel to each other for conjugation to be practical, for resonance to happen. However, because of certain size issues, steric repulsion, the plane of a part of the segment of molecule may turn in a way that now the orbitals are no longer parallel, they become perpendicular to each other. And if they are not parallel, if they are perpendicular to each other, then there is no possibility of resonance, because then the overlap will not be effective to make a pi bond. Okay, so today we are going to understand this topic with a new example. Let us try to first see what is the question number 9, and as you can see on your screen that we have 4 carbene ions. So you can see we have 4 carbene ions, A, B, C and D. Okay, so you have seen the structures on the screen. Now you have to arrange these carbene ions in decreasing order of stability. Now, as you all know, which I have been speaking throughout my videos, that either it be plus charge or it be minus charge, it is a problem. The charge, bearing charge, is a problem, and in order to reduce that problem, you have to do delocalization of the charge. You have to spread the charge, disperse the charge, and this delocalization can be done primarily by resonance effect, and you can also have the minus I effect or plus I effect, which can help you in spreading the charges. Now let us try to see how each case responds to all these tools. So I will start with A. Before I have started A, I have given you some picture, some concept that under what circumstances the benzene ring comes to help you through resonance. So for an example, on your screen you can see that there is a carbon which has a negative charge. So it's basically a carbene ion, and directly with this a benzene ring is attached. So this is a carbon which is attached with 2-methyl group, as you can see like this, and it itself bears a minus charge, and a lone pair is there on this carbon, and it is directly attached with a benzene ring which has a pi system. It has got 3 pi bonds, which I have written as pi system. Now under what condition this minus charge is going to get delocalized in the ring through resonance, through conjugation, is this orbital which is having the lone pair, the carbon which is having the minus charge has a lone pair, and this orbital which bears those 2 electrons, it must be parallel to the 6 pi electrons, or the 6p orbitals, which includes the 6 pi electrons. So this parallel orientation is important for this lone pair to get delocalized into the benzene ring and for resonance to happen. So this is important requirement, that the lone pair carrying orbital must be parallel to all the 6p orbital, as you can see, of the benzene ring, or you can say this lone pair carrying orbital must be parallel to this pi system, like this. It should be like this. If this is a pi system, this should be the lone pair bearing p orbital. They are parallel with each other. Now the lone pair can go inside the ring through the conjugation, as you all know, minus, single, double, and it will start making the resonating structure. So that is the requirement. Now, if by any means you break this condition, you make this orbital carrying the lone pair not parallel to the pi system of benzene ring, and instead of parallel, if the lone pair becomes orthogonal, perpendicular by any means, then there will be no resonance of this minus charge into the benzene ring. So you should understand this should not happen, and if at all it happens, there is no resonance, and that is a situation which we see in steric inhibition of resonance. So let us try to see a different case. Now, if you have NO2 group, okay, so I have drawn the NO2 group as you can see on the screen. This is an NO2 group which is directly attached to the benzene ring. Now, this NO2 group can also do resonance with the benzene ring, and for that to happen, you should understand the plane of NO2. The plane of NO2, this is NO2, you should understand it is trigonal planar. If this is the plane of benzene ring, the NO2 and the benzene ring must be coplanar, and as they remain coplanar, the NO2 and the benzene ring, then what happens? The pi system of the NO2 group remains parallel to the pi system of benzene ring, and then there happens a conjugation double, single, double, single, double, and you can make the resonating structures. The resonance is possible. But if by any means benzene remains like this, but NO2, because of certain issues, for an example, if they come, it turns like this, it becomes perpendicular like this, then as it turns to avoid the steric repulsion, if at all it is present, then the orbitals are no longer parallel to each other. The pi system 1 becomes perpendicular to the pi system 2, and that is the case of steric inhibition of resonance. Then the pi bond of the NO2 will no longer be in conjugation or in resonance with the pi system of the benzene ring, and we will see that this situation will arrive in one or two of our cases. Now, you understand, I have started with the case A. So this is the case number A I have taken, and in the case A, the carbene ion A, you see that this is a carbene ion, a carbon which bears a minus charge. You understand, at the ortho position there are no bulky groups, simple small hydrogens are there, so there will be no problem to these two methyl groups. These two methyl groups which are attached with this carbon, they will not face any potential, any problem with these small hydrogen. There will be no problem of steric repulsion because of these two hydrogens. So what will happen, as I have already told, this group is going to be coplanar with the benzene ring, and a situation like this will come. This carbene ion will remain parallel to the plane of the benzene ring, and the lone pair carrying orbital will be parallel to the pi system of the benzene ring, and the resonance will happen because the two ortho positions, as you can see, have got very small hydrogen which will not pose any steric issues. Now, the problem is not seen on the top, but it is seen at the bottom. So if you see the bottom part, this NO2, you understand this NO2 is, the nitrogen is sp2 hybridized, and Being sp2 hybridized, it is trigonal planar. It tries to flange, it tries to occupy the space from left as well as right. As it tries to occupy the space, the tertiary butyl group, you understand, it's a bulky group with the 3 bulky methyl groups. There happens a repulsion between the NO2, which is trying to remain coplanar with the benzene ring, and this bulky group. So you understand, as there is repulsion, you can see I have written here steric repulsion. This oxygen which is attached with nitrogen, it comes, if at all it tries to be in the plane of the benzene ring, it comes in confrontation, it comes in repulsion with the bulky tertiary butyl group which is adjacent to NO2 group. So it feels lots of pain. So in order to resolve that pain, it tries to go away from that bulky tertiary butyl group, and this was NO2. Now instead of being parallel to the benzene ring, it now turns like this. As it turns like this, the tertiary butyl group which is present in the neighborhood now becomes far from the oxygen. Earlier it was like this, so there was a tussle. As it turns like this, the distance between the oxygen and the tertiary butyl group increases, and it gives relief to the system. The steric repulsion is reduced. So steric repulsion, although has got reduced, but it has to pay some price for that. What is the price it has to pay? The price is, as the NO2 turns, you understand, the pi system of NO2, I have already told you that the pi system of NO2 should be parallel to the pi system of benzene ring for the resonance to happen. But if you have put the bulky groups here, then what will happen? Because of the bulkiness of the group, the NO2 will turn, and as it turns, the pi system of the NO2 will now become perpendicular to the pi system of the benzene ring, and this is not a situation for conjugation. This is a situation for conjugation, that they should remain parallel to each other. They should not be perpendicular to each other. So any problem because of the steric, because of the size, if it occurs, then the NO2 or a similar type of group will turn its plane to avoid that repulsion, and as they do so, they lose the conjugation condition. And that is what is happening in the case A. As you can understand, the case A, the NO2 is not in the plane of benzene ring. So although NO2 is attached, it will not exert resonance effect. So resonance will be absent. Resonance will be absent. What type of resonance will be absent? That means its resonance interaction. The resonance interaction of NO2 group with the benzene ring will not be there because the condition is not met. Okay, so that is one of the issue. Now before we keep analyzing further, I have given a different situation now. For an example, you had a situation like this. This is the carbene ion which has 2 bulky methyl group attached, and at the ortho position, if there is a very bulky tertiary butyl group, as you can see on your screen, then again there is a strong repulsion right here. If the carbene ion tries to remain in the plane of benzene, then from here it feels a strong fight. It feels a strong steric repulsion. So in order to reduce that fight, that repulsion, it has to turn like this, and the moment it turns like this, you understand the p orbital which carries the lone pair now becomes perpendicular to the pi system of the benzene ring. Earlier it tried to remain in the plane of benzene ring, then p orbital was parallel, but because of steric crowding, as it turns, the p orbital also turns, and the p orbital now after turning becomes perpendicular to the pi system of the benzene ring. So now in this case, again it's a case of steric inhibition of resonance, and this minus charge is now not in conjugation, and it loses the opportunity to avail the resonance delocalization. Now the minus charge will not be delocalized in the benzene ring. So delocalization through resonance will not happen because of steric inhibition of resonance. Now after looking at this, again we will analyze A. So after dealing with all the nuances, all the fundamentals, basics, now let us try to analyze A one by one. This is a carbene ion. Ortho position, it has very small groups, hydrogen. So top position SIR is not present, and there will be resonance of this minus charge in the ring. How? Minus single double, and similarly again minus will come here, minus single double. I have already told how to make resonating structure. So the minus charge will certainly come inside the ring, and there will be the three more resonating structures where the minus charge will stay here, it will stay here, and will stay here. So there is a delocalization in the ring. Now what next? The next thing is, you understand, the bottom portion, if you try to see, I have just explained that this NO2, when it tries to remain like this, as I have given here, as you understand, as it tries to remain in the plane of benzene ring, there is a repulsion, and because of that repulsion it tilts, and as it tilts, as it rotates, it becomes perpendicular to the pi system of the benzene ring. The pi system of NO2 becomes perpendicular to the pi system of the benzene ring, and SIR is the outcome, and now it cannot do resonance with the benzene ring because of the steric issues. So partially SIR is present if you see the bottom groups, and top there is no SIR effect. So minus will at least come inside the benzene ring, okay, but it will not go to the NO2 group because NO2 is now in no more conjugation with anything in the benzene ring, okay. So that is important thing. Next thing is to be seen that what is the function of this group. The function of this group is, this is tertiary butyl alkyl group, it's a plus I group. You understand what is the meaning of plus I? It will donate electrons through sigma electrons. What is the job of plus I group? The alkyl group, the methyl, the ethyl, the isopropyl, the tertiary butyl, etc. They just get their sigma electrons towards you. They give sigma electrons towards you. And as they give electrons towards you is not a good thing, because already there is lots of electrons here. Already there is a flood of electrons, and in that flood, if you are giving more electrons, it's going to be a dangerous situation. So in the flood you don't have to give the water. From the flood you have to take out the water. So this is a harmful effect. The plus I effect of tertiary butyl is not helping in the stabilization of the negative charge. Rather it is a demerit. So you understand this resonance is a merit. So I will write it as merit. SIR on NO2, it's a demerit. Why it's a demerit? Because NO2 cannot take the minus charge from the ring and support the delocalization of the negative charge because it is not in conjugation. So it's a demerit. Plus I is a demerit. Now again one merit is there, that NO2 is a minus I group. This NO2 on the other hand is pulling the electrons through the sigma electron. Now it is pulling the sigma electron, and as it is pulling the sigma electron, you understand it's good for the health of carbene ion, because the carbene ion there is excess of electron, flood of electron. So from the flood of electron, you have to take away the electron, because then you spread the charge, you spread the negative charge. So NO2 is going a good job from minus side. Okay, so it's a merit. So it has 2 merits and 2 demerits, as you have seen. At the last of the topic, in final slide, I will write all the 4, will write all merits, demerits, and will compare and get the final result. Now coming on to B, you understand B situation. I have already explained that because the 2 methyl groups are here and this is a tertiary butyl group, it is already a big group, so there is a steric repulsion, there is a fight for space, and because of this repulsion, this carbene ion had to change its plane, and it could not remain parallel to the benzene ring. Had it remained parallel to the benzene ring, the plane of carbene ion, this lone pair which is carried by a p orbital would have been parallel to the pi system of the benzene ring, and a proper delocalization of minus charge would have happened. However, because of this steric repulsion, it loses the battle. It has to avoid that repulsion. It tilts, and as it tilts, its p orbital is now no more parallel to the pi system of the benzene ring, and it loses the resonance contact with the benzene ring, and the minus charge will not go inside the benzene ring. So again, it's a clear cut classical case of SIR. The next, this is what? This is a demerit, because you are not availing the benzene ring for the delocalization of the minus charge, and it had to be done for the stability to increase, which is not possible right now. Now, what about this tertiary butyl group? This tertiary butyl group, as I have told, this is a plus I group. It puts electron towards you. It just gets the electron moving towards you. So already there is a negative charge, a flood-like situation, and on the flood-like situation, if you pour more water, for an example, the situation will be disastrous. So it's not good. So both are demerits based on the B structure, B carbene ion. Now coming on to the C carbene ion. If you see the C has got lots of merit. First of all, as you can easily witness, this carbene ion does not face any trouble from the 2 ortho position, because the tiny hydrogens are there, they pose no SIR effect. So this p orbital which is on the carbene ion remains easily parallel to the pi system of benzene ring, and there is a delocalization, minus, single, double. So minus will come here, again minus, single, double. So you will see minus will come here, minus will come here, and minus will come here. So it's a good delocalization of minus charge that will take place. Okay, this is one thing. So resonance stabilization due to ring you have understood. Now you understand, if the minus charge comes at this position, para, I am drawing that structure, when the minus charge goes inside the ring, and as it goes inside the ring, it when reaches the para position like this, you will see a structure like this, and then since NO2 has no problem from the neighborhood, because in the neighborhood there are tiny hydrogen, so there is no steric issues with the NO2, and NO2 has no problem. Now it will remain parallel to the benzene ring, and the pi system of NO2 will remain parallel to the pi system of benzene ring, and if it happens, it can exert the resonance effect. There is no problem with it. Now how it does it, you can understand. This is NO2, student, you can understand this is NO2. Now you see a conjugation, minus, single, double. So because of this conjugation, you understand this minus charge floats like this, and this pi bond goes like this, and the moment you do this, you get a resonating structure like this. You get a good resonating structure. Why I am saying it's a good resonating structure? Because now it will have the minus charge on the oxygen, Earlier what happened, the minus charge were remaining on the carbon. When the minus charge was delocalizing inside the ring, it always happened to be on the carbon. But this is the structure where NO2 participated. It pulled the minus charge from the ring and put it on the oxygen, and oxygen being much more electronegative than carbon is very able to hold that minus charge. As you all know, a resonating structure where minus charges on more electronegative element is a better structure. So because of this, it is very efficiently delocalizing the minus charge. So the NO2 is doing that. Not just that, you understand one thing more I want to add. NO2, I have told, has got minus I effect. What does it mean? It means that it pulls the electrons through sigma bonds. So it pulls the sigma electrons, and it is good for the health of carbene ion, because you understand there is a situation, floodlight situation on the carbene ion. If you pull out the water from floodlight situation, it's good for the situation. So both the things, the resonance delocalization of the minus charge in the ring, the resonance delocalization of minus charge on NO2, and the minus I effect, making this carbene ion the best carbene ion amongst the 4 possibilities. I will finally take up all the 4 options and will compare in the last slide. Okay, now coming on to the carbene ion D. You understand the carbene ion D, I have already said. Now there are 2 small tiny hydrogen. They say, I will not pose any problem to you, dear carbene ion. You can easily get your p orbital parallel to the pi system and avail the resonance, avail the delocalization, and the similar happens, the same thing happens, minus single double, and again minus single double, again minus single double. So there will be a good delocalization of minus charge. However, the minus charge will be confined within the ring, because there is no extra NO2 type of group which you have appended to the benzene ring, which could get the minus charge towards it. It can pull so that it could pull the minus charge from the ring and take it on itself. There is no NO2 like group, so it will remain confined to the ring. So in this sense, the C had a merit. There NO2 was also present. This is a merit, that resonance stabilization due to ring will happen, but apart from this merit, it has a drawback as well. As you understand, this is a tertiary butyl alkyl group. It has a plus I effect, and what is the meaning of plus I effect? It pushes the electron, it pushes the sigma electron towards the side where already there is abundance of electron. There is a proliferation of electron, there is a flood-like situation, and on that if you are adding extra is dangerous for the health of the carbene ion. You should understand. So one merit you have and one demerit you have. Okay, now we have all seen all the cases A, B, C and D. We have analyzed all the merits, all the demerits. Now we will sum up all those things in a single slide like this. Now be very watchful while I am explaining. Now you understand, if you take up A, the minus charge got delocalized inside the ring. So ring was helping in delocalization. However, because of the steric repulsion, NO2 could not help in delocalization of minus charge because of SIR effect. It turned perpendicular to the ring to avoid the repulsion. So SIR effect could not get the help of NO2. However, NO2 still had the minus I effect. There is no need of parallel orientation for inductive effect, because it is not operating through the pi bonds, it operates through the sigma bond. So there is no issue like this. So minus I is there and is good for the health. But one drawback is there. The plus I effect of tertiary butyl makes the thing less stable. Okay, so the merit is there, the demerit is there, the merit is there, and demerit is there, as I have already spoken about. Now let us see the structure B. In B, what happened? The there is no resonance, you understand. The minus charge remains localized at this carbon. It even does not go to the benzene ring. Why it does not go to the benzene ring? I have already told, because this is a bulky tertiary butyl and there is a methyl group, there is a steric issues, so it turns its plane and becomes misoriented with the pi system of the benzene ring. It becomes perpendicular, the p orbital becomes perpendicular to the pi system of the benzene ring. So the resonance delocalization is hampered, is not happening, and that is a problem. Apart from that, you understand, first of all, now ring is also not taking the electron through resonance. Second of all, the tertiary butyl group is there, which is electron pushing group. It is pushing the electrons to sigma electron and making the flood situation even dangerous. Why? Because already there is abundance of electron. You had to take the electron away, not to give electron in that situation. Okay, so both the situations are harmful. So you understand, B is seen to be the least stable one, because in any measure it is not getting the merits. Now coming on to the C option, I have elaborated it that it is the best possibility. Why? Because the minus charge is in conjugation with the ring also. Once the minus charge comes at the para position, it goes in the NO2 also. So there is a widespread delocalization of minus charge, and not only that, it does not has any tertiary butyl group which could have given the electron through plus I effect. So the demerit is also not there, and apart from that, the NO2 group which is present has got minus I effect. So all the positives are there and the negatives, the demerits are not there. So obviously the C is the best one, and the D, you understand, has got the ring participating in the resonance, but again it lacks NO2 which is present in C, so there is a difference in that sense. And apart from that difference, it has got tertiary butyl group which not taking but giving the electron, which is not good for the health of the carbon, because it already has lots of electrons. Okay, so after reading all these simple features and comparing all, we have come to a conclusion that C is the king. Okay, after C, you understand, the A comes. Why A comes? Because ring is participating in the resonance, and apart from that, NO2 is exerting minus I effect. Okay, although in the D the ring was participating, but NO2 was not there, and minus I effect was not there, which could have stabilized the carbon ion more. So after C will come A, and after A will come D, and finally the struggling one is the B, because not just it lacks the ring resonance, it also lacking in the NO2 group, and apart from that, to make the situation worse, it has the tertiary butyl group which is feeding electrons to a place where already there are lots of electrons. You did not want to make it more dense. You had to take the electrons away. So this is how that is how you are going to see the comparison, the features, and that is what I have done. I hope you must have understood all the basic fundamentals I have included to explain all these 4 carbene ions. And in a similar manner, we will keep on doing different topics in GOC, and will take up all the variety of problems in doing so. Till then, take a good care of yourself. Thank you very much.